Hey everybody, this next video lesson is going to talk about the VSEPR model. The VSEPR model is a three-dimensional model of molecules, and so we get a closer look at what the molecules look like in three dimensions: the vertical, horizontal, and the depth component. Lewis dot structures only give us a two-dimensional or flat version of a molecule, but now we incorporate the third dimension. Now the basic premise of the VSEPR model is that there's a central atom, and then there are things called ligands, or elements that are bonded to the central atom. And they are going to try to minimize electron repulsion around the central atom to spread themselves out as far as possible. Now there are two types of domains around the central atom. There's a bond domain and there's a lone pair domain. Take, for example, water. Water has a central oxygen, and it has two bonds to the two ligands of hydrogen down here, and it has two pairs of electrons. Now the bonds we call bond domains, and the electron pairs are called lone pair domains. Now in typical circumstances, there can be no more than 4 domains around the central atom, but that's only if an element sticks to the octet rule for the central atom. But I'm going to show you, and this is AP chemistry, so this exists more likely than you think, that there can be more than 8 electrons around the central atom, and that is what we call expanding the octet. Now before we begin taking a look at each one of these VSEPR models, I'd like to point out that you'll need to know the structures by memory, the names of them, and also the relative bond angles. And when I say relative bond angles, what I mean is an estimated bond angle. But that'll be more clear to you as we describe what's happening here moving forward. Here are the steps involved in being able to apply the VSEPR model. First, you need to have an accurate Lewis dot structure, which represents the bonds and electron dots around the central atom. The next thing you want to do is take account of how many electron domains there are around that central atom. Now, we talked on the last slide about how there are bond domains and electron pair domains, or lone pair domains. They all count as one domain. So if there is 2 bonds and 2 pairs of electrons around the central atom, that counts as 4 total domains. From there, you can then predict the shape. When predicting the shape, the first thing you need to do is identify the central atom. And then you count total domains around the central atom, counting all bonds and all pairs of electrons that are touching the central. Next, you want to take a look at those domains and ask yourself, are they bond domains or electron pair domains? Because bond domains and electron pair domains may result in a different shape. I'll explain it to you using the different pictures on the following slides. The following tables can be found on page 337 of your textbook. I grabbed some screenshots and I put them in the slides here. Now on the last slide, I talked about how you want to make sure you count the total number of domains around the central atom. And so this first number here in this table is total number of electron domains. Now the first picture is not the molecular geometry. The molecular geometry is the final shape. What this first picture shows us is just what the electron domain geometry is. In other words, if we treat bonds and pairs of electrons as the same, then this is the shape of the domain geometry. And that is different depending on when you add a third domain or a fourth domain, and we're going to show in the next slide, we're going to get to 5 and 6 domains as well. The first thing you need to know is that there's 2 domains, then they always form a linear electron domain geometry. These 2 domains will always lie 180 degrees across from one another, and that is the bond angles that you're going to have to know by memory for the electron domain geometry only. So 2 domains are always 180 degrees. Now, there's no other way besides bond domains in order to do 2. You can't have 1 bond and 1 non-bonding pair of electrons. We're going to call non-bonding domains electron pair domains. But they always are bond domains when there's just 2. You can't have 1 of each. Now, as a result, the electron domain geometry matches the molecular geometry. The molecular geometry is the actual 3D picture of what you're going to need to know for the quiz and test. There are multiple shapes that you need to know, and these are the ones you're going to need to know by name. An example of one that has 2 domains, both of which are bonds, is the carbon dioxide molecule, with a central carbon and a pair of bonds on the left and the right-hand side, always at 180 degrees away from each other. Now, as we move down, you'll notice that we're going to add another domain. And every time you add a domain, you add another potential shape or another potential molecular geometry to the table. Now again, starting with the electron domain geometry, it's a very broad representation of the molecule. If we're treating all the bonds and all the electron pairs equally, well then those three domains are going to spread themselves out. And if you spread themselves out around a circle, you're going to get each one to be 120 degrees apart from one another. Now, the first example is if all of the domains are bonds with no electron dots. If that's the case, then the domain geometry matches the molecular geometry. And that's the case for all of these shapes. If the domains are always bonds, the domain geometry matches the molecular geometry. But what happens if you replace and cut off one of these bonds on top and replace it with just a pair of electrons? Well, then you still have three domains, as you see. You still have two bonds plus one electron equals three total domains, but you no longer have 3 and 0. You have a combination of 2 and 1. And if that's the case, you get what we call a bent molecule. So the shape here is called bent, and it's because it looks like it should be a straight line, but it's got a little bend. Now what happens is, you would think that these atoms are all going to lie in a straight line because, well, there's only two bonds and they always want to be equal distant from one another. But this pair of electrons here on top has a repulsive force and pushes the bonds down at an angle. And as a result, it gets out of line. It's called a bent line, bent linear. Some textbooks might refer to the shape as bent linear, but this one just calls it bent. It should be in a line, but because the presence of the electrons on the top push the bonds down at an angle, resulting in an angle of about 120 degrees. Now, it's not just that a pair of electrons will be the only things that result in electrons being repelled. This pair of electrons that are made up of this bond in the trigonal planar molecule likewise are pushing the other two bonds down so that they are all equal distant from one another. These electrons are all repelling each other around the central atom, and they're all going to sit as far away from each other as possible. And so these bonds and electron domains have a repulsive effect on each other. They are always pushing each other away from the other one so that they're evenly spread out around the central atom. Now, in truth, a pair of electrons has a larger repulsive force than a bond domain. But I just want to be clear that a pair of electrons would cause this angle of the bent molecule to be less than 120 degrees. Now, in the trigonal planar, since they're all bonds around the central atom, this is 120 degrees. But for a bent molecule, replace a bond with a pair of electrons, and the angle becomes more sharp and becomes less than 120 degrees. But for your purposes, for memorizing bond angles, you simply need to remember that for the domain geometry, the bond angle is 120, assuming that electrons and bonds have equal repulsive factor in a three-dimensional molecule. But of course they don't. Now, this third picture on this page is when you've got four domains all equally spread out around the central atom. And instead of going vertically and then down and to the left and down to the right, now we have four. And so you need to think about this in 3 dimensions. This is the first electron domain geometry that utilizes the third dimension. These first two were pretty flat. Linear is flat, trigonal planar is flat, but tetrahedral has a depth component to it. Now, if you have 4 bonds and all the domains are in bond form and no pairs of electrons, well, I mentioned before, your domain geometry is tetrahedral. Your actual shape, your molecular geometry, is also tetrahedral. An example being the CH4 molecule, or methane, also known as natural gas. Now let's replace the top of the hydrogen, cut it off, and replace it with a pair of electrons. And now you've got 3 bonds and a pair of electrons. Remember, that pair of electrons counts as a domain, so it's one of the 4 domains, but it's not the same as having a bond there. And so the shape changes. We cut off the top of the tetrahedral and replace it with a pair of electrons, and the resulting shape is known as trigonal pyramidal. Finally, if you take off not just 1 but 2 arms of this tetrahedral molecule, you get something with 2 arms and 2 pairs of electrons. And 2 with 2 still add up to be 4, but the combination of two bonds and two pairs of electrons result in, once again, something called a bent molecule. Now, bent is used for two bonds and two pairs of electrons, or two bonds and one pair of electrons. Both are identified as bent shape. Now, the domain geometry results in a bond angle of about 109.5 degrees. 109 would be fine, but if you wanted to be more specific, the exact angle would be 109.5. And that would be the same as the bond angle in this tetrahedral molecule. But remember, a pair of electrons have a greater repulsive force, and this angle would be, the bond angle right down here would be less than 109.5, because those hydrogens would be closer together, resulting in a more acute bond angle. But again, for our purposes, you only need to worry about 109.5 as the relative bond angle for 4 domains. Now, 4 domains is going to be the maximum amount of domains that could be around the central atom if the central atom is fairly small. If it's in the second period of the periodic table, it's only going to be limited to having 4 domains. But once you get down to the third period of the periodic table, if you have something like sulfur or phosphorus or silicon as the central atom, you're going to be able to expand the octet to more than just 8 valence electrons around the central atom. And you can get upwards of 5 or 6 domains, meaning 10 or 12 electrons that are at or near or touching the central atom. The next slide is going to show you the shapes that result when you expand the octet. So let's talk about 5 electron domains. If you've got 5 domains around the central atom, you're expanding the octet because each domain represents 2 electrons, and 5 times 2 equals 10 total electrons. So you are past the octet rule when it comes to drawing Lewis dot structures. Now, the central atom, once again, has 5 domains around it. And if all 5 domains are bonds, then the electron domain geometry matches the molecular geometry, which, once again, this is called trigonal bipyramidal. It's called trigonal bipyramidal because it's like you have 2 trigonal pyramidals sitting base to base. Imagine you have 2 pyramids that are 3-sided, and then you pick them up and you stick them together at the base so that they have a shared base. Then you've got this diamond-looking shape that has a 3-sided pyramid on top and a 3-sided pyramid on bottom. That's why it's called trigonal bipyramidal. Now, the bond angles for this electron domain geometry is the only one that has 2 possible bond angles. Because if you zoom in on this and you take a closer look, you have the bond between the vertical and the horizontal domains, and then you have the bond between the 2 horizontal domains, and they're not equivalent to one another. In fact, the bond angle between the vertical, which I'm going to call the polar domains, because if you imagine on a globe, this would be the North Pole and this one being the South Pole. The angle between the pole and the equator is 90 degrees, right? The angle that you would expect between something going vertical and something going horizontal would be 90 degrees. And so if you are looking at the bond angle of the polar versus the equatorial domains of this electron domain geometry, it's 90 degrees. But if you're looking at the bond angle between one equatorial domain, which I'll highlight in red, and one equatorial domain, which I'll highlight in blue, those are not sitting 90 degrees apart from one another. If you look at them from the top, if you can use your spatial brain, you'll see that it's basically split up into a triangle. And if you take a circle and split it up into 3 pieces, then these, once again, are 120 degrees. And so it has 2 bond angles, one for the vertical and one for the equatorial. Now let's zoom out here and get back to what we were talking about. So when you've got 5 bonds, the trigonal bipyramidal matches the domain geometry. Now you replace one of those domains with a pair of electrons, you'll get a new shape. That new shape is called seesaw. Now it might not look like it right here, but if you were to model this using the little ball and stick models, it would make more sense to you, because when you lie it on a table, it forms a little seesaw. It's actually quite fun to play with. But that's the name. It's called seesaw. Now you might be wondering, well, does it matter which bond gets replaced with a pair of electrons? And the answer is yes. I'm going to zoom in once again on the screen so you can see a piece of the picture. the pair of electrons that gets added in replacing a bond is always going to be one of those equatorial domains. Never a vertical domain, always one of the horizontal plane domains. And because of that, you still maintain this 90 degrees here, and you still maintain the 120 degrees here, and you will only remove a bond and replace it with a pair of electrons on that horizontal plane, the equatorial plane. So 4 bonds, once again, results in something called seesaw, as long as you have 4 bonds with 1 pair of electrons. Now replace another bond with another pair of electrons, and you get what is known as T-shaped. And you can see again how it gets T-shaped because you keep the 2 vertical domains, the North Pole and the South Pole, and you've replaced 2 of the 3 equatorial domains, and so you've got, well, basically a big letter T. It's on its side, but it's T-shaped, and that's literally what it's called. You think, well, that's pretty basic, right? Well, yeah, it is. Scientists don't always have to make up more complicated things than they have to, and this is called T-shaped, with 5 total domains, 3 bonds, 2 pairs of electrons. An example being chlorine trifluoride. If you got chlorine in the middle and 3 fluorines on north, south, and then 1 on the equator, you've got a T-shaped molecule. Finally, the last combination you get would be 2 bonding domains and 3 pairs of electrons. So imagine you've taken the domain geometry up here and you've replaced all 3 equatorial domains with pairs of electrons. What you get is just a central atom and 1 up and 1 down and 3 pairs of electrons, all 120 degrees from one another here in the center. What you get is back to linear. Well, it makes sense because you just got a North Pole, a South Pole, and the central atom, and those all line up in a straight line. And an example of that would be xenon difluoride. And now you're looking, hey, wait a minute, xenon's a noble gas. How is that possible? Well, we say that noble gases have very low reactivity, but they are no longer considered non-reactive elements. And some of the larger ones, as you move down the group, where the electrons get further and further from the nucleus, and you now have something large enough to expand the octet, you can now make bonds with things that are noble gases in the middle. And xenon difluoride is the example. It's pretty rare, but it's possible. Finally, we'll go to 6 domains. If you've got 6 domains, let's zoom in on this picture and get a closer look. You've got 1 up, 1 down, and then 4 making a nice square along the equator. If we're going to use the terms polar and equatorial again, well, you've got 2 polar, north and south, and you've got 4 along the center plane, the equatorial plane. Now, because these are all evenly spaced out from one another, these are all perfectly 90 degrees separate from one another. The vertical and horizontal and the horizontal up from the other horizontal all are 90 degrees from one another, and so you only need to remember that 1 bond angle there. Now, if you take and make all of those domains bonds, well, then you get an octahedral domain geometry that matches the octahedral molecular geometry. Octahedral, octa means 8, and if you take a close look, you basically have an 8-sided polygon. You have 4 sides on top, 4 sides on bottom, stuck base to base. Imagine 2 4-sided pyramids stuck base to base. Trigonal bipyramidal is 2 3-sided pyramids stuck base to base. Well, octahedral would be 2 4-sided pyramids stuck base to base. And you've got yourself octahedral. Now replace one of those bonds with a pair of electrons, and you've got 6 domains, 5 bonds, 1 pair of electrons. It doesn't matter if it comes off a vertical or a horizontal domain because they're all treated equally because they're all 90 degrees apart from one another. So you take one, let's just call it off the bottom and replace it with an electron. Then what you get is called square pyramidal. It's a pyramid with a square base, and that's why it gets the name square pyramidal. Now, when it comes to removing a second pair of electrons off of this octahedral domain geometry, the place that happens does matter. If we take one off the bottom, then we've got to take the second one opposite of that to keep the symmetrical look of this molecule. And so the 2 pairs of electrons that are going to be on this molecule come off opposite sides of one another. And as a result, all you get is a square. And this is what we call square planar. An example of square planar, once again, would be something if you've got xenon in the middle with 4 fluorines on the outside. Again, it's pretty rare, like the linear that you saw up above with the 5 domains being linear, it's just as rare to find something that has 6 domains but 2 pairs of electrons and 4 bonds. And once again, that only happens, or pretty much only happens, when you've got xenon in the middle. But it happens, and you have to know it. So here's a summary slide of the bond angles that you need to know by memory for the quiz or the test. Remember, the bond angles are based only on the electron domain geometry and not the molecular geometry. So for the linear, where you've got 2 total domains, the bond angle is 180 degrees. For the trigonal planar, you've got 3 domains, and those 3 domains separate themselves at 120 degrees apart from one another. The tetrahedral is 4 domains, and those all occupy a space in 3 dimensions at 109.5 degrees from one another. Now, when we expand the octet to 5 and 6 domains, we start to get some bond angles that are a little bit strange. Trigonal pyramidal, once again, has a 120 degree bond angle between the equatorial domains and a 90 degree bond angle between the vertical and the equatorial domains. So there are 2 bond angles that you need to be aware of for trigonal pyramidal. And octahedral, you have 6 arms coming off the central atom, all at 90 degrees from one another. Now, I mentioned this before, but a lone pair actually takes up more space and has more repulsive factor to it in the molecular geometry than a bond pair does. So when you have a pair of electrons, say, on the central atom with 2 bonds, the angle is not going to be 120 degrees. The actual angle will be less than 120 degrees. Now, you'll have to know that little bit of information, but you won't need to be able to identify the actual bond angle. You may be asked, what effect would putting a pair of electrons on the central atom compared to a bond do to the bond angle? And you say, well, normally it'd be 120, but a pair of electrons takes up more space and repels more, so the bond angle would be slightly less than 120. So you just qualify it by saying less than. And the last thing you need to know is that multiple bonds take up more space than a single bond. Imagine multiple bonds. A double bond is basically putting 4 electrons really close to each other in one area or one domain of the molecule, and those will have a greater repulsive force. Now, this is pretty rare, and I, in fact, have never seen this before in the AP test, but just for your information, multiple bonds would take up more space than a single bond. An obscure example of this would be something if you've got like POCl3. You might remember this molecule from a previous video lesson when we were doing Lewis dot structures and resonance structures. But you've got a phosphorus in the middle. Now, there's still only 4 domains because you've got 4 sides of the phosphorus that are surrounded by electrons. Now, phosphorus was able to expand its octet, so there are 10 total electrons occupying 4 domains only. So based on VSEPR shape, there's only 4 domains, so it's tetrahedral electron domain geometry. And the fact that they're on all bond domains means that the molecular geometry is also tetrahedral. But if I were to draw this or model this, this pair of electrons, this double bonded O, actually has a greater repulsive force than a single bonded O would be. And so it has more repulsive force and pushes the chlorines. So the chlorines are all going to they're all going to kind of clump in closer to each other at an angle closer than or smaller than 109.5 degrees. If it was a true single bond between the oxygen and the phosphorus, it would be a nice even 109.5 around them. But because there's 2 pairs of electrons there, it's going to squeeze the bond angle between the chlorines at less than 109.5. Let's try a couple practice problems to check to see if you understand what's going on. Feel free to pause the video right now, jot these down in a notebook, and I'll go through the answers here shortly. First thing we want to do for this first one is draw a Lewis dot structure. So you've got carbon in the middle, and you've got hydrogen left and nitrogen right. The nitrogen is going to be triple bonded to the carbon, the hydrogen is going to be single bonded, and there's a pair of electrons on the nitrogen. Now there are 2 domains, and both of which are bonds, so this is going to represent a linear molecule. And linear domain geometries are always 180 degrees as far as the bond angle is concerned. Now this next one is pH3. You're going to have P in the middle, and you're going to have 3 H's coming off the phosphorus with a pair of electrons on the central phosphorus. So you've got 4 domains, but you've got 3 bonds and 1 pair of electrons. So this molecular geometry is trigonal pyramidal. But the domain geometry is tetrahedral, and tetrahedral are always bond angles of 109.5. Remember, we're treating the pair of electrons the same as a bond in the domain geometry, so that means that there's only one bond angle that you have to worry about when it comes to tetrahedral domain geometry. Now this last one is going to expand the octet. We've got sulfur in the middle with 4 fluorines on the outside. Now we've got to make sure that we account for all the valence electrons. Sulfur has 6, and 4 times 7 is 28, giving us 34 total electrons. Now 8 of those are used up in bonds, so that means I've got 26 dots, so 24 of them can go on the outside fluorines, which means, yes, sulfur can expand its octet, and that puts a pair of electrons on the central sulfur. Now if I count the total domains around the sulfur, I have 5 domains. Now since those 5 domains are not all bonds, I can't just say it's trigonal bipyramidal. Its domain geometry is trigonal bipyramidal, but it's got a pair of electrons instead of a bond. So if I remove a bond and replace it with a pair of electrons, what I get is seesaw-shaped. But the domain geometry is trigonal bipyramidal, as I just mentioned. That means there are 2 bond angles. It's not very clear on this Lewis dot structure because of the way I drew it, but we've got a vertical fluorine, and it's 90 degrees from one of the equatorial fluorines. But then I'll highlight the equatorial domains. We've got 3 of them in blue, and those are all lying 120 degrees from one another. So there are 2 bond angles that you have to worry about for 5 domains, the trigonal bipyramidal. I'm going to finish up with a couple of thought-provoking questions. This one is a true or false question. It says a molecule that has polar bonds will always be polar. Go ahead and pause the video and think about this. If true, explain why. If false, provide a counterexample. Well, I'll tell you, the correct answer here is false. And here's how. I'm going to go back to my old trusty friend, carbon dioxide. So carbon dioxide looks like this, CO2 with a double bond left and a double bond right. And it's got linear shape. It's linear domain geometry and linear shape. Now the bond itself is polar, and the dipole points out towards the oxygen because oxygen's more electronegative. But the bond pulling right is equal to the bond pulling left. And because of the shape of the molecule, these 2 bond dipoles cancel one another out. So if you've got a bond that's polar, but it's also being counterbalanced by another bond that's polar, or even 2 or 3 more bonds that are all pulling equally but in opposite directions, the polar bonds may result in a nonpolar molecule. Well, that takes care of this video lesson. Thanks for watching.